So today we continue to talk about this Laplace transform, which is a generalization of the Fourier transform. You can think of it as applying a decaying exponential to the original signal before you perform the Fourier transform, so that you are able to accommodate more types of signals compared to the original Fourier transform. Okay. Now, last time we talked about several properties of the region of convergence. We can quickly go through some that we talked about last week. So first of all, we know that the region of convergence must consist of strips parallel to the j omega axis in the S-plane. And this is mainly because whether or not the transform converges at a point S depends mainly on the real part and not on the imaginary part, okay? Because the real part determines how fast this exponential is decaying, either in the positive or negative axis, okay? All right, and then for rational Laplace transforms, the ROC cannot contain any poles because at a pole this transform becomes infinity, basically saying that it's not convergent, okay? So the RLC cannot contain any poles. Now the third property says that for any finite duration signal that is absolutely integrable, the RLC is the entire S-plane. This is because when you have a finite duration signal that is absolutely integrable, then no matter what type of decaying exponential you're multiplying onto the signal x of t, it would still be absolutely integrable. Okay. All right. So property 4 says that if you have a right-sided signal, a signal like this, right, that extends only to the right, then the region of convergence must be the right half plane. And this is because if you have this right-sided signal, and you say that the signal multiplied by this decaying exponential with exponent sigma 0, right? Suppose that this right-sided signal multiplied by this exponential is has a Fourier transform, then multiplying it by a decaying exponential that decays even faster than that of sigma naught should also converge, right? So if it converges for this, when you multiply it with this curve here, then any other exponential that decays even faster should also converge, okay? And that corresponds to points, to the right of sigma naught, okay? So if a signal is right-sided, then the region of convergence must be the right half plane. Now similarly, if your signal is left-sided, right? If your signal is left-sided, then it must be the region of convergence must be the left half plane for the same reason as we just discussed, okay? Now when your signal is two-sided, right? A two-sided signal you can actually view as a left-sided signal plus a right-sided signal, okay? So for a left-sided signal, the region of convergence must be the left half plane, right? Something like this, right? The region of convergence must be the plane to the left of some value, let's say sigma L. And for the right-sided signal, the region of convergence must be to the right of some value sigma R, okay? So the overall signal x of t, the region of convergence for this overall signal x of t should be containing the intersection of these two regions, which will end up to be a strip, right, if it exists, okay? But it's possible that if sigma L is less than sigma R, then there may be no region of convergence, meaning that the Laplace transform does not exist in that case, okay? And last time we looked at an example for this, all right? So here we have this two-sided exponential e to the minus bt, okay, absolute value of t. So if b is greater than 0, then it decays on both sides. But if b is less than 0, it increases on both sides, okay? Now, assuming that b is less than 0, assuming that b is greater than 0, then, through this derivation, you find that the region of convergence, so this Laplace transform exists for values of s, with real part between minus b and b, okay? So when it's, decaying on both sides, you get a region of convergence that is this strip here. But if b is less than 0, then b becomes less than minus b, meaning that there is no region of convergence, and therefore the Laplace transform does not exist, okay? And that is reasonable because, if you look at a signal like this, if you multiply it by a decaying exponential that decays to the right, then it's possible to suppress this part of the signal, but this part of the signal still goes to infinity, okay? Now, you can say I can try to multiply with an exponential that decays to the left, but if you do that, then you're suppressing this part of the signal, but the right part still goes to infinity, okay? So no matter what exponent you choose, you're never able to suppress, both sides sufficiently to get a absolutely integrable signal, okay? All right, so concluding all these points that we just mentioned, we get the following summary, okay? So we know that if the region of convergence exists, then this region of convergence must be only one of these four possible cases. It can be either the entire S-plane, it can be the left half plane, the right half plane, or a single strip, okay? It can be the entire S-plane, the left half, the right half, or a single strip, okay? So, all right. So what corresponds to the entire S-plane, right? Like we mentioned in a previous property, a finite duration signal, right, would have a ROC that is the entire S-plane, right? So finite duration, okay? And what would have a left half plane as the ROC is a left-sided signal, okay? A right half plane will correspond to a right-sided signal, and a single strip will correspond to a two-sided signal, okay? All right? Okay. So it can only be one of these four possible cases, either the entire plane, the left half plane, the right half plane, or just a single strip. Okay. Now, furthermore, you can show that if the Laplace transform is rational, then its ROC is bounded by poles, either bounded by poles or that it extends to infinity, okay? So if it's rational, then it is either bounded by poles or extends to infinity, okay? So this means that, your region of convergence will extend to infinity if there are no poles blocking the way, okay? But if there is a pole along the way, then you will be bounded by that pole, right? Your region of convergence can only extend up to that pole, right? And if there are no poles, you can go to infinity, all right? All right. So then if the Laplace transform x of s is rational, then if x of t is right-sided, right? If it's right-sided, we know that in general, the region of convergence should be the right half plane, okay? But from property 7, we know that if it's only the right half plane, then it means that to the left, it should be bounded by the pole, okay? By a pole. So if x of t is right-sided, then the ROC is the region in the s-plane to the right of the rightmost pole. Okay? So if it's rational, now if we know it's right-sided, then the ROC is the right half plane. So it means that on the left side, it is bounded by the rightmost pole. Okay? So similarly, if your signal is left-sided, if it's left-sided, then the ROC is the left half plane, which means that on the right side, it should be bounded by the leftmost pole, okay, by the leftmost pole. Okay. So knowing these properties allow you to sort of characterize what the signal may look like by just observing its poles and zeros and the region of convergence on the S-plane. Okay? Now let's look at an example. Okay. So suppose that we have a Laplace transform x of s that is equal to 1 over s plus 1, s plus 2. Okay. So if you look at this, right, this signal has two poles, one at -1 and one at -2, right? Okay, so this signal has two poles, one at -1 and one at -2, okay? So these two poles. Okay. Now, if you have two poles like this, then there are only three possibilities for the ROC, right? You can either have an ROC that is to the right of the rightmost pole, okay? To the right of the rightmost pole, which gives you this, okay? So you can be to the right of the rightmost pole. Okay? Or you can be to the left of the leftmost pole. Or you can be a strip in between two poles. Okay? So if your Laplace transform is rational, then your region of convergence can extend all the way to a pole, right? And if there's no pole, you can extend to infinity. Okay? So for example, in this case, you extend to infinity on this side, but you extend only up to the pole on the left, right? So in this case, you extend to infinity on the left, but you can only extend up to the pole on the right, okay? And in this case, right, you extend to both sides, but both sides are bounded by poles. Okay. Now, maybe you can ask, for example, in this case, right, why is it extended only up to the leftmost pole, right? Why can we not have a left half plane that is from this point to the left? Okay. So why can we not have a plane that is to the left of this one? Okay. So the thing is that if your region of convergence is to the left of this point, then it will include a pole, right? And the pole is definitely not convergent, right? Because the value of x at the pole is infinity, right? Okay. So looking at this, you can obtain the poles, and given the poles, you know that there are only 3 possibilities corresponding to this Laplace transform. Okay? Now, if it looks like this, which has a RLC that is the right half plane, then you know that the time domain signal must be right-sided. Okay? So if it looks something like this, which is the left half plane, then you know that the time domain signal is left-sided. And in this case, x of t is 2-sided. Okay. Now, the Fourier transform is a special case of the Laplace transform for a choice of s on the imaginary axis. Okay? So to see whether or not a Fourier transform exists, we simply have to observe whether or not this imaginary axis is in the ROC. Yes. Yeah. So in this case, the Fourier transform exists, but in these 2 cases, the Fourier transform does not. Okay. Okay. So for both of these cases, the Fourier transform does not exist since the j omega axis, basically the imaginary axis, is not in the ROC. Okay. All right, so this is the Laplace transform. Okay. Now, given the Laplace transform, the question then is whether or not we can reconstruct back the original signal x of t, similar to doing an inverse Fourier transform. Okay. So how do we do this inverse Laplace transform, similar to that of the inverse Fourier transform? Okay. So the idea is actually quite straightforward, relying on what we learned for the inverse Fourier transform. Okay. Now suppose that this is the Laplace transform at a point s equal to sigma plus j omega, okay, in the region of convergence. Okay. So suppose that this is the Laplace transform at the point s equal to sigma plus j omega. All right. Now, as we mentioned previously, the Laplace transform, okay, at this point is equivalent to taking the Fourier transform of x of t multiplied by this decaying exponential e to the minus sigma t, okay? So if you write the Fourier transform out, this is what you get, right? So the key here is to understand that the Laplace transform is actually just a Fourier transform, but evaluated on x of t times this decaying exponential e to the minus sigma t. Okay. So if we understand this, then how do we take the inverse Laplace transform? Okay. So if this is the Fourier transform of this, then this means that we can get back this x of t times e to the minus sigma t by taking the inverse Fourier transform of this. Okay? And the inverse Fourier transform is defined as follows, right? It's 1 over 2 pi, the integral of this function of omega times e to the j omega t d omega. Okay? So then, if you just multiply this to the other side, then you get an inverse Laplace transform. Okay? So if you multiply this to the other side, then x of t, you get x of t here, okay? And then you get, e to the sigma plus j omega t, right? I'm multiplying this to the other side, so I get a sigma here, all right? But, here, this integral is in terms of omega. So I just need to perform a change of variable to convert it back to s, okay? So I just perform a change of variable, where we set set s equal to sigma plus j omega, okay? And this is what we get, right? So when we perform this change of variable, originally we're integrating omega from minus infinity to infinity, okay? But now we should be integrating s, right, from sigma minus j infinity to sigma plus j infinity ds, right? And there's a j here to compensate for this j here. Okay? So what is the Laplace transform? The inverse Laplace transform. The inverse Laplace transform is the integral of x of s times e to the power st integrated over this line this line corresponding to the real part of s equal to sigma. Okay? So this line, right, this vertical line in the region of convergence. Okay? So the Fourier transform is just a special case. The Fourier transform is just a special case of the Laplace transform. Okay? So suppose that we have a region of convergence that looks something like this. Okay? So if you perform a Fourier transform, right, you're mapping your signal x of t, right, to a function x of j omega, which is defined on the line on this imaginary axis. Okay? But when you're performing the Laplace transform, right, you're converting x of t, you're representing x of t with x of s, right? For assuming that s is sigma plus j omega, then you're representing the signal with the values of capital X on some line corresponding to the real part of S equal to sigma. Okay? So this is saying that you can actually reconstruct the original signal by integrating along the line, along any line in the region of convergence, and you should be able to get back this signal, okay? So you don't necessarily have to integrate over this imaginary line, but any line, integrating over any line in the region of convergence allows you to get back your original signal. Okay? So this is, much more general than the original Fourier transform. Okay. Right. Now, when you integrate over some line on the complex plane, right, you're performing some type of contour integration, which could be, tedious at times. Okay. But we often do not need to actually work out this contour integration because for many problems we can just, obtain the inverse transform by observing the patterns of what it looks like in the Laplace transform. Okay, so this is similar to what we did in the Fourier transform case. Right. So this is one example. Okay. So in this example, right, just by observing the form of the Laplace transform, we should be able to obtain what is the inverse Laplace transform. Okay. So suppose that this x of s is this 1 over s plus 1 times s plus 2. So similar to what we do in the case of computing the inverse Fourier transform, the first step is to split this into two terms using partial fraction expansion. Okay. So if you use partial fraction expansion, you can find that this is equal to 1 over s plus 1 minus 1 over s plus 2. Okay. Now here we have the algebraic, these two algebraic expressions. Okay. Now for a Laplace transform taking on this algebraic expression, right? We know that there are two possibilities for the region of convergence for this term here. One is to have a region of convergence greater than -1, right? To the right of -1, which is the pole here, or to the left of -1. Okay? So for this term, there are two possibilities for the region of convergence. One is for the real part of s less than -1, or for the real part of s greater than -1. Okay. Now similarly, for this second term, the region of convergence can be either the real part of s less than -2, or the real part of s greater than -2. Okay? So if you look at this term here, right, which has a pole at -1, then the region of convergence can be either the right half plane to the right of -1, or it can be the left half plane to the left of -1. Okay? So similarly for this term, the RLC can be either the right half plane to the right of -2, which is the pole, or to the left of -2. Okay? But only one of these is true. Okay? Now, how do we decide which one should be true? So we can observe what is the region of convergence for the original Laplace transform. Right? So we see that this should have a region of convergence that is greater than -1, okay? Which means that in this region, both of these should exist, right? Both of these exist. So that is only possible when the region of convergence for this is this one here, and the region of convergence of this is this one here. Okay? Okay? So for both of these terms to hold under this region of convergence, their corresponding region of convergence can only be this and this, okay? Which are the right half planes. All right. So if you know that, right, if you know that the algebraic expression for this term is 1 over s plus 1, and you know that the region of convergence is the right half plane, then you immediately know what is the time domain signal. Okay? So if you know that this is s plus 1 with region of convergence that is greater than minus 1, then you immediately know that this is e to the minus t u of t. Okay?